Hello, in this video I am going to give demo of these three collabs simultaneously with comparison of how am I building a three hidden layer neural network for nonlinear regression using synthetic data with three input layers by PyTorch Scratch no built-in layers, and also with PyTorch class based in built-in, and also PyTorch Lightning. These three have a similar steps but with little change in the variables or the process that we use, but they all three have a similar steps that I can show in comparison simultaneously. So let's start with the notebook B. So here in the first markup cell in all the three notebooks, I have mentioned what are the steps I would be doing in further, or what is the synthetic equation used in this particular notebooks. We can see these are the different synthetic equations. These are all the steps I would be doing for the each notebook that which I have given in a bullet points. So let's start with the first cell, and here I install the required libraries for this notebook. I use PyTorch for building and training the neural network, and scikit-learn for train test split and PCA, and matplot library for plotting the data and results. So here also it's the same thing that I'm using, and here I'm using I use PyTorch Lightning. One extra more thing, because this is for the PyTorch Lightning building for the high level training structure. Otherwise rest of the libraries are similar to other notebooks. Then in the second cell, I import the required libraries and set the random seed so that the results are reproducible. So as we can see here, right? Then I generate a synthetic nonlinear regression data using three input variables x1, x2 and x3. Then target y is created using nonlinear equation with sign terms, polynomial terms, interaction terms and some noise. So this gives me a nonlinear regression problems. After generating the data, I combine the three input into future matrix X, reshape the target and split the data set into training, validation and test sets. Finally, I print the shapes of the splits to verify that the data has been divided correctly. So we can see that I have split all this like training, validation and test data, and these are the shapes of it. So it's the exact same thing for the other two notebooks too. Here we can see I have imported a numpy as variable, x1, x2, x3 are the three variables, y is the target, and I combine all these three variables into the future matrix X, and then reshape it and split the data set into training, validation and test set, and these are the shapes printed. So exact same thing for the PyTorch Lightning notebook 2. Here three variables, target, combine into matrix, reshape and then split it into three variables along with their shapes. Next is 4D style plot. In this cell, I create a 4D style visualization of the dataset because the problem has three input features and one target variable. So these are the three features and one target variable, which is y, and it is effectively four dimensional. To visualize it, I use PCA to reduce the three input feature into three principal components, which is PCA1, PCA2 and PCA3. So the same thing for here these three notebooks too. Then I plot these three components in 3D space, and I plot this and I use the color bar to represent the target value, which is y. So the point position shows the transformed input features and color shows the output. Here we can see on the x-axis there is like PCA1 component, on y-axis PCA2 and PCA3. This is the color bar which represents a target y. Here also the same thing is plotted and a similar thing here. Next, here in the next cell, I import a PyTorch and then set the PyTorch random seed and check whether the GPU is available. If CUDA is available, the model can run on GPU for the faster execution, otherwise it runs on CPU. Then I convert the train, validation and test datasets into PyTorch tensors and move them into to the selected devices. But in next, we'll go to the next notebook and see what am I doing here. Here also is a exact almost same thing that I'm doing. So what am I doing is, in this there's also I'm importing the torch and also set the PyTorch random seed, and if CUDA is available, the model can run on GPU, otherwise it runs on CPU. Then I convert the similarly train, validation and test into PyTorch tensors and move them into the selected devices. And we can see which device we are using device is CPU. We'll go to the next notebook and see. So here also, so we are kind of doing the same thing here. So what we are doing is similarly PyTorch, tensor dataset, data loader, and extra thing is PyTorch Lightning. We can see. So these are the important libraries that we are trying to import here. So similar to the previous one, I convert the train, validation and test into PyTorch tensors and wrap them into a data sets and data loaders. And the reason for using data loaders is that Lightning expects batched data during training and validation. That's the reason this is one extra thing that we are doing for the PyTorch Lightning. Next, for the next few steps, I'll define for this particular notebook. And in this cell, what I do is I define these next steps are for like defining network dimensions. In this cell, I define the architecture of the neural networks. The input dimension is 3 because sample has 3 features. Then I define 3 hidden layers with size 32, 24 and 16. Finally, the output dimension is 1 because this is a regression problem and the model predicts one continuous value. Let's see what happens to other here. Here also we can see like we are defining a linear one with 32, 24 and 16 sizes of these hidden layers along with the ReLU here. And finally, even the output here, like dimension is 1 because this is also like a regression problem. So let's see what happens here. This is exact same thing that's happening here too. Next, let's see manually initializing trainable tensor. What happens here? So this is the core setup of PyTorch from scratch version. Here I manually create the trainable parameters of the network, weights and biases for the first hidden layer, weights and biases for the second, and for the third layer, and then for the output layer. Each parameter tensor is created with required grad true, which tells PyTorch is track gradient for it. The important point is that I'm not using built-in layer classes like nn.linear here. I am defining all parameters manually, which makes this a true scratch implementation. And I would go to the next notebook C and see what's happening here. So after setting a dimension 3, 32, 24, 16 neurons and one output neuron regression, I also have used ReLU activation of each each hidden layer. This version is more structured than the Scratch version because PyTorch handles the parameters registration automatically through nn.module. And in this cell, I create an instance of the model, move it to the selected devices, then I define the loss function as mean squared error because this is a regression problem. I also define the optimizer usual atom, which updates the model parameters during the training. And I'm also going to like after I say print the model, then it is going to give me for sequential what are the features, and for ReLU, and it's like in future and out future and then BIOS. These are the values that are printed in a whole. Now let's go to the next notebook and see what's happening here. And similarly how we have set, so after setting input size, first, second, third hidden layer, Here also I have used ReLU activation for the hidden layer. Then I define the forward method, which explains how the input moves through the network. I also define training step, which tells Lightning how to compute the training loss for each batch. Validation step, which computes validation loss, and configures optimizers, which returns the optimizer, usually Adam. So Lightning organizes the same training logic into a cleaner and more reusable structure. In this cell, I also create an instance of lightning model. Then I create a lightning trainer object. The trainer controls the training process, including the number of epochs, hardware usage like CPU or GPU, and logging behavior. This is one of the main advantages of the lightning. Instead of writing the full training loop manually, I define the logic in the module and let the trainer handle the repetitive boilerplate. Next step, what am I doing? Next is the training progress. Next is training step. Okay, so in this cell contains. mm, okay, let's see what happens next. um, I run the forward pass on the training data here, and I compute the mean squared error loss, call the backward. So PyTorch AutoGrad computes gradients, upgrade the weights and biases manually inside a Torch NoGrad block, and then clear the gradients before the next epoch. I store both training loss and validation loss over all epochs. So in this notebook, PyTorch is handling the gradient computation automatically, but I'm still controlling the network structure and parameter updates manually. Uh, yeah. So I think I have to mention even a few points here for this notebook. I would say here, yeah, let's go to this layer. In this cell, I'm defining the forward pass of the neural network. The input goes through the first linear layer followed by ReLU, and second linear layer followed by ReLU, and the third one, and then the final output layer. The layer is linear because this is a regression problem. So even though I am not building using a built-in PyTorch layer objects, I still build the full 3 hidden layer neural network manually using tensor operation. And then here also I would like to mention few more points. I am defining a loss function here, and learning settings I'm doing here. Since this is a regression task, I'm using a mean squared error loss, and I have also defined a learn rate, which we can see here, that controls how the parameters are updated during each training set. So let's go to the next notebook and see what's the training progress here. So here, for a training, this cell contains the training loop for the class-based PyTorch model. And for each epoch, I set the model to training mode, run the forward pass on the training data, compute the loss, clear any old gradients, call loss backward to compute gradient, and update the parameter using the optimizer. After that, I switch to evaluation mode. For validation, compute validation loss and store both training and validation losses. This is much cleaner than the scratch version if you observe, because built-in layers and the optimizers simplify the code. Next, what am I doing is I'm printing the uh, training progress here. So what to say here is like I print the training loss, which we can see here, and the validation loss at regular intervals. We can see the intervals here, so I can monitor the learning process properly. Let's go to the next uh, notebook. Here for the training one, um, this one is done. So I'm going here, like for training the model. In this cell, I start by passing the model training data loader, and training data loader, and then validation data loader to the trainers. And Lightning then automatically handles the epoch loops, the batch processing, the gradient computation, optimizer step, and validation evaluation. So compared to regular PyTorch, this version is much shorter and cleaner because the framework manages the repetitive training workflow. In the next cell, I check the log training or validation metric after training. So doing this, what is the useful? We can see here. This helps confirm the model has trained successfully and let me inspect the final loss values. Okay. Now that these things are training part is done, let's see what are the next steps. Next is loss curve plots. So in this cell, I plot the training loss and validation loss over epochs. This help me check whether the model is learning properly and whether the validation performance follows the training performance. Okay, next let's see the curve here. In this cell also I plot the training and validation loss across epochs. This helped me to see whether the model is learning properly and whether the validation performance is close to the training performance. Even in the next, okay, okay, here we are not doing it actually. Okay, let's go back to the PyTorch Scratch no built-in one. So here now let's see regression matrix helper and then plotting the final metrics. So in this cell, I define helper function to compute final regression metrics such as mean squared error. Sorry. Uh, okay, we'll go. Okay, okay, messy and root mean squared and mean absolute error and r squared. These metrics give a numerical summary of the model's final performance. So now finally let's test predictions. In this cell, I turn off gradient tracking using Torch Snowgrad and run the trained network on the test set. Then I convert the predictions from PyTorch tensors into NumPy arrays so I can evaluate and plot them easily. So finally, here I print the final regression metrics for the test set. These values show how well the PyTorch Scratch model predicts unseen nonlinear regression data. The final step of this whole for this notebook of PyTorch Scratch no built-in layers is I create a scatter plot comparing the true target values and the true target values and the predicted target values. If the model has learned the nonlinear relationship well, the point should lie close to the ideal diagonal relationship. So this gives a visual confirmation of the final model quality. Let's go to the next notebook and see what's happening there for the same regression matrix helper cell. So in this cell, I define a helper function to calculate final regression metrics such as mean squared error, root mean squared error, mean absolute error, and r squared. These metrics are used to evaluate the final model performance on the test set. So in the final test prediction, I switch the model to evaluation mode and turn off gradient tracking. Then I run the train model on the test set and convert the prediction into NumPy arrays for evaluation. Next, in the next cell, I print the final, so here are the final metrics, and these values show how well the class-based PyTorch neural network predict unseen nonlinear regression data. Next is true versus predicted scatter plot. In this final cell, I create a scatter plot of true target values versus predicted target values. If the model has learned nonlinear mapping well, the point should be close to the ideal diagonal relationship. So this gives a visual confirmation of the model's final regression performance. So similar to that, here also, in this also I define a helper class and I have all these values errors here, and then these matrix are used for the final evaluation of the test set. Yeah, similar to what I did previously, then I can switch the model to evaluation mode and generate the test set and then I convert the prediction to NumPy array so I can compute the final regression. Next, we can see here I print the final regression matrix metrics for the test, and these values show how well PyTorch Lightning model predicts unseen nonlinear regression data. So in this final cell, after doing all those metrics, we can see the scatter plot comparing the true target values and predicted values are given here. And also we can see that the points are almost close to the diagonal, and which shows that the model performs well. And this gives a visual confirmation of final regression performance. And if I have to summarize all these things together, what I would say is, here in this notebook of PyTorch Scratch no built-in layer, I implemented a hidden layer nonlinear regression neural network in PyTorch from scratch, and I manually created all trainable parameters and did all the steps, and finally I evaluated the final model, which I have done similarly to all other two steps too, like PyTorch Lightning and PyTorch class based building. And while explaining through the process, I have also showed how Lightning is different from other, and how PyTorch class based built-in is similar to the previous steps, but also how organized or they are better than the PyTorch scratch no built-in one too. So yeah, that's it with the demo of these three notebooks, and thank you.